So thank you again for joining us for tonight's presentation, 3 minutes on the future of energy. We are pleased to partner with and feature researchers from the U of A's Future Energy Systems area. My name is Colleen Elliott, and I am the Manager of Education and Special Events in the Office of Alumni Relations. We acknowledge that the University of Alberta is located on Treaty 6 territory and respect the histories, languages, and cultures of First Nations, Métis, Inuit, and all First Peoples of Canada, whose presence continues to enrich our vibrant community. Our speakers today will give their presentations in video format, and the video is approximately 15 minutes. Afterwards, our 5 researchers will join us for a live Q&A session. You may submit questions throughout the presentation. Simply type it in the Q&A box, which probably appears at the bottom of your screen. Again, you can input those at any time. We will have approximately 45 minutes after the presentation to answer some of your questions. I would like to acknowledge one of our special guests this evening. In our audience today is the President-elect of the Alumni Association, Mr. Tyler Hansen. Tyler, thanks so much for joining us for our first virtual alumni weekend. I also have the very great privilege of introducing President Flanagan, another very special guest joining us tonight, and it is my pleasure to introduce our new President and Vice Chancellor, Bill Flanagan. He is the 14th President and Vice Chancellor of the University of Alberta. President Flanagan served as the Dean of Law from 2005 to 2019 at Queen's University. He was President of the Council of Canadian Law Deans from 2011 to 2014 and served on the National Action Committee on Access to Justice in Civil and Family Matters. His work in support of HIV/AIDS research and initiatives has made him a well-recognized and respected public figure. President Flanagan, thank you so much for joining us tonight.
Well, thank you, Colleen, and welcome everyone. This is actually my first alumni event as president, and of course, with COVID, our ability to get together has been restricted. But I just want to thank Colleen and all of the very talented staff at Alumni Relations for thinking very creatively about how we can still gather in the time of COVID. And I was looking at the program that's been put together for the week, and it's really outstanding. So I just want to thank all of the staff, and of course welcome all of you, and also tell you how much I look forward to meeting our alumni in person once we're able to do that. As Colleen mentioned, I'm the newly minted president here at the University of Alberta, and it's also a homecoming for me as I grew up in Alberta, and I'm really thrilled to be having returned home and joining such a wonderful university community. And tonight, of course, we're talking about energy. And energy has been a research priority at the University of Alberta since the 1930s, when Carl Clark first developed the process for extracting oil from the oil sands. And although I did not grow up in the 30s, I hasten to add, I do remember a time of growing up in Alberta and hearing about the oil sands and about this wonderful resource. If only we could crack the nut to remove this resource from the sands, it would mean a whole era of prosperity and growth for the province of Alberta. And while we did crack that nut, and we cracked that nut at the University of Alberta, and it did lead to an era of tremendous prosperity. And of course, I saw that as a young boy growing up in Alberta, and all of the benefits and opportunities that brought to the province. And since that time, thousands of our alumni have contributed to our society's understanding of energy, whether through the lab, the workplace, or through their communities. And today, our energy research program ranks them first among Canadian universities and in the top 20 worldwide. Energy systems is one of our institutional signature areas of research strength and teaching. And the centerpiece of that research program, and you're going to be hearing a lot about that tonight, is our Future Energy Systems Research Program. And it is funded by the largest single research grant in the history of the university, $75 million from the Government of Canada. So this is a real jewel in the crown of what we're doing here at the University of Alberta. More than 650 graduate students are part of Future Energy Systems. And as you will see tonight, their work is both highly advanced and highly diverse, exploring not only the technology of energy, but the societal implications of our changing energy systems. So you'll see when we talk about energy systems, that last word system is particularly important. It means that we're not just researching better technologies for harnessing energy. It means we're considering the environmental, economic, and social implications. We're asking how our society's relationship with energy can evolve. The centralized industrialized energy system that we rely on today was first imagined during the Industrial Revolution. New technology makes it possible to decentralize energy, to reduce its environmental impacts, and perhaps even to reshape our communities and how we live. Through our energy systems signature area, our researchers and students are exploring all of these ideas. And over the next hour, you will meet 5 simply brilliant young scholars from 5 different disciplines, all working on pieces of this vast, complex energy systems puzzle. I hope you will enjoy this sample of energy systems research currently underway here at the University of Alberta. I can tell you I am very proud of what we're doing here at the university and the enormously talented faculty and students that we're able to draw. So on that note, let us begin the presentation. Thank you.
This is not a secret, but we currently need oil and gas to produce energy. Thanks to oil, we can not only run our cars, but also heat our houses and pave roads, produce electricity, drugs, clothes, and many other good things. Hello everyone, my name is Elena Andriianova, and I am a PhD student at the University of Alberta. I am doing research in petroleum engineering. Canadian engineers are spending days and nights to find the most environmentally friendly methods of oil production. One of the big challenges of oil production in Canada is that the most of our oil is crude oil and bitumen, which is so dense that cannot flow without our help. Imagine honey. We have liquid or solid types. The same with oil. Conventional liquid oil can be produced easily, but unconventional bitumen is thick and cannot flow easily. So it needs to be treated before making possible to extract it. How we can help it to flow? We have 2 options: to heat it, as in steam-assisted gravity drainage, or we can dissolve it by use of solvent, as in BEPEX technology. These are the main methods of bitumen production. Unfortunately, they have drawbacks. The heating-based techniques inject hot steam under the ground, so a lot of water and energy are required, making the process not so environmentally friendly. Solvent-based methods are more ecological because they require less energy and water, but they work slowly, so are less profitable. The solution is the combination of heat and solvents. These methods are promising, but we still need to study them. How we can study these methods? The best way is computer modeling or simulation, when we make a computerized copy of an oil reservoir and test any desired production technique on it. If the model is small and simple, the simulation time is just seconds, but thermal solvent-associated techniques are quite complicated. So it can take days and weeks to run a single model. This makes it hard to perform testing. So my team develops a statistical upscaling method which will make models work faster under these complex conditions, but still stay accurate. By making it easier and faster to test oil production processes, we can help oil sand companies identify more environmentally friendly and ecological ways to produce oil that we all use every day. Using artificial intelligence techniques, including machine learning, my team trains computers to quickly and accurately simulate the real-world effects of changing parameters. This helps us to understand how different design, such as solvent types and flow rates, could affect the productivity of the well. This will minimize the environmental impacts of our current energy system, while our society makes the transition to a new energy system. Thank you so much for your attention.
Researchers predict the global energy consumption along with its associated CO2 emission will increase by at least 25% over the next 50 years. With the increasing energy demand and awareness of global warming, the entire energy market is trying to transition from fossil fuels to renewable energy such as wind and solar power. Although the renewable energy sources are much more sustainable and environmentally friendly, they do suffer from the intrinsic intermittency. That is, their power output not only depends on location, but also time of the year or even time of the day. This results in an imbalance between the supply and demand in electricity. But what if we can build a giant battery that stores electricity when there's energy surplus and releases energy when there's energy deficit? This brings us to my research. My name is Yingjie. You can call me Jay. I'm a fourth-year PhD student at the Department of Chemistry at the U of A. My research primarily focuses on developing catalysts for battery applications, specifically zinc-air batteries. In addition to being low cost and extremely safe, zinc-air batteries can store 4 times as much energy as the current lithium-ion batteries. These benefits make zinc-air batteries an ideal candidate for stationary energy storage. However, the chemical reactions inside the zinc-air batteries are very slow. This lowers the potential and power available to the external device, also known as potential and power output. Therefore, current zinc-air batteries require platinum ruthenium as catalysts to speed up the reactions and increase the potential and power output. But the high cost and scarcity of this precious metal greatly impede the large-scale commercialization of zinc-air batteries. My project is to design and produce efficient and cost-effective catalysts as an alternative. The alternative catalyst I produced is a hybrid between hollow mesoporous carbon nanospheres, or HMC in short, and manganese oxide nanoparticles, both of which are much cheaper than a platinum ruthenium. Here is their electron microscopic image. The hollow structure of the HMC and the nanoscale size of the manganese oxide nanoparticles maximize the effective surface area of the hybrid, which ensures maximum interaction between the catalyst and the reactants inside the battery. To evaluate catalysts in zinc-air batteries, we look at their potential and power output. When a catalyst is incorporated into the battery, higher potential and power output indicate a better catalyst, which we found here with the hybrid in comparison to the original HMC and the precious metal platinum ruthenium. We also found that the hybrid showed a minimal discharge potential drop after 120 hours of cycling, indicating a highly stable material. This means that the battery can be recharged many times while still maintaining the same amount of energy storage capacity. In conclusion, not only does this hybrid catalyst reduce the cost of zinc-air batteries dramatically, but it also exhibits higher potential and power output, as well as superior stability than their precious metal counterpart. This is an important step in making renewable energies more feasible and make sure we have the energy we need without the carbon dioxide we don't. Thank you for listening.
Global warming, climate change, greenhouse gas reduction, and energy transition are large and complex problems facing the world today. Given their magnitude and global impact, we often search for large-scale, top-down solutions to address these problems, overlooking that some answers may lie closer to home. Good evening. My name is Neelakshi Joshi, and I'm a postdoctoral researcher at the University of Alberta. My research deals with municipal and community-level climate action. The scale of cities and neighborhoods that we live in is important to understand, as this is where a large demand for energy is concentrated and where a majority of the greenhouse gas emissions emanate. Edmonton, the city where my research is centered, has one of the highest per capita greenhouse gas footprints in Canada, an unflattering 19 tons per person against a global average of 4.4 tons. However, the city has launched an ambitious energy transition plan to bring down per capita emissions to 3.2 tons per person by 2035 and aims for carbon neutrality by 2050. It plans to do so most by focusing on everyday issues like promoting denser neighborhoods with carbon neutral houses and encouraging electronic vehicles. My research analyzes how this transition plan addresses local contextual factors like the existing availability of and the reliability on fossil fuels, legislative and financial limitations, and a high culture of consumption. But do Edmontonians need to wait for the government to make changes in their carbon footprint? Based on my research into volunteer-led neighborhood organizations called community leagues, the answer is no. Certain neighborhoods in Edmonton and their citizens have initiated bottom-up action long ago through community leagues. They are adopting renewable energy for community buildings and investing in energy-efficient retrofits. Furthermore, volunteers regularly organize workshops and information sessions diffusing the understanding and adoption of low-carbon technologies deep into their neighborhoods. We are working in collaboration with these pioneer neighborhoods to develop long-term climate action plans to sustain and amplify this initial momentum. While neighborhoods and city-level efforts may seem small compared to large global problems, it is a combination of such small efforts that contribute back towards achieving national and ultimately international level greenhouse gas reduction targets. Thank you.
We all love summer. Imagine yourself driving on a country road, enjoying the sunshine, seeing the beauty of the landscape full of trees or crops. This reminds us about the beauty of our Mother Nature and inspires us to take actions to protect her better. However, what if I tell you that our daily life, especially driving, is emitting lots of carbon dioxide, which is adding burdens to our environment? Actually, over the past 60 years, the carbon dioxide content in the atmosphere has increased by over 30%, resulting in sea level rise, extreme weather, etc. One major contributor to this massive CO2 release is our consumption of fossil fuels, such as coal or gasoline. To help solve the problem, my research focuses on developing a novel fermentation technique for a very promising biofuel production, the alcohols. Specifically, I am developing the technique of SCF, self-cycling fermentation, for the production of the alcohols. Our research features 3 advantages. Number 1, we are not competing with food. SCF is designed to deal with various types of agriculture and forestry wastes, such as wheat straw, corn stover, sawdust, wood logs, etc. These wastes can generate sugars, and SCF can convert the sugars into alcohols. Number 2, high productivity. Current industry operates alcohol fermentation on a batch-to-batch basis, while SCF is a semi-continuous operation, which runs the fermentation much faster. As a result, we have shown that SCF can produce over 70% more alcohol each year compared to current batch method. Number 3, highly integrated and automated system. We have designed a software program to manipulate the fermentation process. With a computer, we can not only inspect but also control the fermentation process. This can significantly reduce the labor intensity, making it more financially viable for the industry. So far, we have demonstrated SCF in a small flask of 5-liter bioreactor, and we wanted to scale it up to 100-liter pilot level. With SCF, we are confident that we can help contribute to the protection of our environment. Thank you.
Hi everyone, I'm Maggie Cascadden, and I'm excited to present our research team's project to you. Our project is a life cycle analysis of novel materials and processes, and it's about the process of sustainable innovation. We're from the business school, so this project brings a business lens to the cool emerging technologies that other researchers are developing within the Future Energy Systems research program. The Future Energy Systems Initiative is all about understanding, designing, and evolving our future energy system so it looks the way we want. An important part of this is innovating solutions to clean up what's going to be left behind by our current energy system. In truth, this is a very difficult task. Otherwise, we would have already done it. And part of the solution will have to include technologies that haven't yet been fully researched or developed. Our team is specifically looking at the cool technologies that are being developed for constructed wetlands designed to clean up oil sands processed water. The first part of our study is to understand what energy, chemicals, and human power these technologies take to be manufactured, and the kinds and quantity of pollution they create. To do this, we're conducting something called a life cycle analysis. This is a method of accounting for all the inputs and outputs of a product making process, so you can add these up and see the full impact of that product on the environment. Inputs include things like water and energy, and outputs might include waste, heat, and chemicals. This is what it looks like for one of the technologies, Biochar, and as you can see here, there are many steps, and it's quite complicated. If you look at this other novel technology based on chicken feathers, it's even more complicated. The life cycle analysis software can generate estimates of material usage and waste products based on an inputted version of these maps. And it's important to conduct these kind of analyses so that we know the impacts of the technologies we're creating. That's our first major goal. After all, these technologies are not going to help us create the kind of future energy system we want if their production causes a worse environmental impact than what we're trying to clean up. In addition to all that, it's important that these technologies are economically viable if we want them to be real solutions that we can actually get out into the field and adopted by industry. So the second important part of our project is to identify which of these technologies have potential to be commercialized. Once we understand the life cycle of the new technologies, we can understand how much they're going to cost to produce. Our goal for this project are threefold. First is to identify which technologies are going to be the most beneficial for oil sands processed water cleanup. Second is to identify which technologies are economically viable and commercializable. And ultimately, we want to help scientists and engineers who are working on the best technologies get their work out of the lab and into the field. Thank you.
All right, thank you so much to our 5 researchers. As you can see, there's quite a diversity of research that's going on. Lots of different ideas in the hopper, and hopefully we'll be able to bring some of them to fruition soon. Thank you again to our panelists for those video presentations. It can't be very easy to put all of that information into a 3-minute presentation. So we have the Q&A session now, which will allow our audience opportunity to ask more in-depth questions and to learn more about those different research areas. At the bottom of your screen, you'll find the Q&A icon. Please click on that and then enter your question there. We will not be using the chat box for the questions. To moderate this portion of the evening, we are joined by 2 members of the Future Energy Systems team. I'm pleased to introduce Valerie Miller, who is the Outreach and Engagement Coordinator for Future Energy Systems. Valerie graduated from the University of Alberta with a PhD in land reclamation in 2019. So she will also be available to answer questions that you have about land reclamation. Kenneth Tam is the Communications Manager with the Future Energy Systems and has been with the program's executive team since its launch in 2017. Kenneth and Valerie, I'll turn it over to you to moderate our Q&A section.
Thank you very much, Colleen. So just a note to everyone, I'll ask our panelists to turn on their cameras and microphones. Basically, the way this question and answer is going to run, because we expect a lot of questions, is Valerie will be reading out a question that comes in via the question box, and then I'll be directing that question to our panelists, and then if more than one of our panelists want to weigh in, we'll be able to make sure that everybody gets their chance.
So our first question is, how computationally demanding is machine learning? Do you need special computers for it?
Well, I think Elena, that's probably a good question to bring to you first because machine learning is such an important part of the modeling you're doing of reservoirs. But actually, I probably want to put that question to everybody because you're all using computers at a certain point. So Elena, why don't you talk to us about the machine learning and the modeling you're doing, and then we'll go from there.
Oh, hello everyone. This is a very good question. And for example, for our team, normal computer is okay, but of course it depends on the problem. If like we are solving huge problem, which is like for the production, like we have to combine all the data from a huge amount of data, maybe we will need some more powerful stations. But for now, for our research, just regular computer is okay. Maybe it will require more time, but it's still enough for us. Like that's why we are doing optimization. That's why we are doing machine learning and optimization, because if we will just start solving the problem without using machine learning, it might take like weeks and months to solve something. But with machine learning, it will be easier. And for example, we can leave some processes to be solved without us, for example, overnight. And this is much more easier with the use of these technologies.
Very good. So I guess, Maggie, you're next on my version of Zoom. So when you're doing those life cycle analyses, do you have any sense of the computing power that's going into those?
Yeah, they're actually, we're able to use an open source lifecycle analysis software that's usable on any computer. So if you're interested, it's called OpenLCA and you can just check it out online, anybody.
Excellent. Jay, when you're looking for different catalysts, are you doing a lot of software work or is it a lot of experimentation in the lab?
My work is mostly wet chemistry, so it would mostly be lab work. But I do know some of my colleagues do some modeling and simulation to kind of predict what kind of combination of catalysts will work better than others. And I think, I don't think our modeling or simulation requires supercomputer. If we really need better or higher computing power, we can simply go to Amazon or Google, who actually offer this kind of services.
Very good. And then, Gia, you said that you can use a computer to sort of, I guess, hack the fermentation process. So is that just a regular computer or do you need more processing power as well?
It's just a regular computer.
Very good.
Yeah.
And then, Neelakshi, not to leave you out, but I'm guessing a lot of the work that you're doing with community leagues, I mean, you're probably just using a computer on email, but correct me if I'm wrong, please.
So we do use computational power because we most of our work is done through interviews and surveys. So definitely basic computational power is needed. Yeah.
Very good. Okay, well, we may end up talking more about machine learning and computation and so forth, but Valerie, do you have another question for us?
We have a lot more questions. The next question is, how extensive are the possible uses of the biofuels being developed?
Well, that sounds like a good question for Gia to take on. So do you want to take the first crack at that one?
Yeah, actually, biofuel is not a new thing in the world anymore. So there are two big countries producing the ethanol in the world. The first one is the US. They mostly produce alcohol, which is the ethanol from corn. That's the major feedstock they have been using, and they are now the largest ethanol producer in the world. And the second one is Brazil. They use sugarcane to produce ethanol. Well, they are at the very, we call it first generation ethanol, because they use mostly our food-based feedstock. And now the society and the whole world are trying to move to a second generation, which is lignocellulose biomass, which is agriculture and forestry waste I have mentioned in my presentation. And they are mostly the waste feedstock. And while that technology, it has been commercialized, but some the starting up companies failed. So it's the technology is getting back and forth. So I'm saying it still has great potential to reduce greenhouse gas emission. The technology is awesome, but we're still working on that to make it fully cost competitive.
Well, I don't know. Maggie, do you want to weigh in on the business side of biofuels at all, or is that outside your area?
That's outside of my research here at the business school, a little bit, yeah.
No pressure, it's okay. Valerie, do you want to throw us another one?
All right, the next question we have is, how do you dispose of the batteries once they're too old? Can you recycle the catalysts? I believe this was related to Jay's research.
Jay, do you have anything to say on that one?
Yes. So it depends on what kind of battery catalyst we're using. If it's metal oxide related, we can definitely recycle the metal part. We can simply dissolve them in acid and then recover them in terms of metallic metal or metal oxide themselves. But carbon, in terms of carbon, is a little bit more difficult to recycle because after the cycling, they're very likely to degrade. And because of the battery design, we use a very basic aqueous electrolyte. Therefore, the carbon degradation will speed up in that kind of electrolyte. And afterwards, the morphology as well as the chemical structure of the catalyst will change. So that would be more difficult.
Very good. Does anybody else want to weigh in on that? I'm guessing it's outside your areas of expertise. Okay, then Valerie, another question, please.
All right. Do community leagues have the authority to enforce rules about energy efficiency to its members?
I think we know that's going to Neelakshi. I don't even need to say anything.
So very good question. So the answer is yes and no, because they do have direct control over their own buildings, and that's where community leagues have started. So they have started off with their own community halls as well as recreational facilities, and trying to power that with solar and so on. Whether they can enforce it in the wider community, yes and no, because they do have a certain say over infrastructure that comes into the community. So if, let's say, there is a retrofit project on replacing streetlights in the neighborhood, they can influence the city to adopt LED lighting, for example. However, the problem gets a bit tough when it comes to private property development. Their community leagues do not have a direct say. But the hope is that once this idea of neighborhood initiative sort of takes root, and a neighborhood imagines itself to be a carbon neutral neighborhood, future they could be in a position to sort of influence future construction. But that's definitely a thing to look at, and would be needed if large scale change is needed at a neighborhood level. I hope that answers the question.
Sounds good to me. Valerie, do you have another question for us?
Is there any funding input for your respective projects from the private industry?
I can speak more on Future Energy Systems' behalf. We don't have any direct partnerships with private industries, but individual research groups, for instance, might be working with private sector companies depending on the nature of the research. I don't know if any of you or any of your groups have relationships with private industry that you can talk about, or anybody? No? Okay, so it very much varies depending on what the technology is, what the state of the research is. Some of our research is very fundamental, so like Jay in the lab looking for new catalysts, and some of it is much more applied and much closer to being put out in the field. But the five here, I mean, recognize that the 5 speakers tonight represent less than 1% of the graduate students working in Future Energy Systems, so it's only part of the picture of the work we're doing, and so hope that helps answer your question. Valerie, another question?
Maggie, how many technologies are you looking at in your LCA?
Well, thanks for the question. So right now we're focused on 2 technologies. One has to do with chicken feathers, and one has to do with biochar. And the chicken feathers technology, there's sort of just one main type. The biochar, we're looking at 4 different variants of the biochar technology. And within those, there could be other factors that we use a different LCA to look at, like different heat levels that the biochar gets to, and other small details like that. So 2 umbrella technologies, but within the biochar, there's at least 4, and you could even break it down further.
That's great. And I know some of the other research groups in Future Energy Systems are doing life cycle analyses on different technologies. So it's something that needs to be done on a lot of different technologies. Valerie, more questions?
To what degree can the SCF technology be scaled, given its semi-continuity versus singular batches?
Go ahead.
Yes. Yeah, I guess that question is definitely for me. Yeah. So ideally, there's really no restriction. So we are comparing SCF with a conventional batch. So any type of batch bioreactor, any size, we can give a try with the SCF, because with our system, there's barely any reconstruction of the reactor. Because it's just the operation process is a little bit different. The infrastructure stays the same. So I would say ideally any scale, but right now we were able to, I mean, during my PhD study, I was able to scale from a small flask to a 5-liter bioreactor.
Perfect. Valerie, next question.
All right, this is one for probably all of you. Should we go all in on one type of energy or diversify the energy infrastructure?
Okay, well, Maggie, I'll throw to you first since we were just talking about LCAs, but everybody get your answer ready for this one.
Yeah, I think just like the basics of setting yourself up for the future, you want to diversify your portfolio, and that includes like setting up your future energy system. If you put all of your eggs in one basket, you end up being very reliant, and that basket, if anything goes wrong, you're kind of stuck. So you really want to diversify, and so I'd say it's a good idea to do that with future energy plans.
Seeing some nods there. Who wants to weigh in on that one next? Jay, I see you next in line.
I agree with the previous answer, and I also think the future of energy will definitely be a combination of various energy sources, renewable such as solar and wind, maybe nuclear energy if people are comfortable with that, and also a little bit of fossil fuel. Because even nowadays with today's technology, even if we have a super battery or that can capture solar power and wind power and can store the energy density or the power input and output may not be competitive enough in comparison to fossil fuel. For instance, aircraft fuel and also gasoline car nowadays are still cheaper than electric cars. So yeah, in the future is definitely a combination of various sources.
Any other perspectives? Maybe Elena, do you want to weigh in on this one?
I suppose that if we want to be independent, we need to be ready to use everything that we can. For example, we can not only rely on fossil fuel, because like we need to support all the industries. And I don't know, like if we have wind power, and if something happens and we cannot use them anymore, we should have something in our pocket to be ready to use something and not to leave the people without energy supplies for some moment. And of course, if we will use our technologies, if we will grow our technologies, we can also sell them to somewhere else. And it is always good for the country and for the communities in general.
Gia, obviously you're working on biofuels, but what would your perspective be on different or diversifying our sources of energy?
I will be on the same page with Maggie. I'm totally up to the diversity, because if we only rely on one source, if one day something breaks, we don't have any energy source anymore. So I'm totally up to the diversity.
And Neelakshi, I'm curious from the perspective looking at community leagues, do you think a diversity of sources would make it easier for community leagues to be engaged in their own energy development?
Absolutely. And I go back to what President Flanagan mentioned in the beginning. He talked about not just diversification in terms of sources of energy, but also the way it is distributed, and to think about micro generation and so on. So that neighborhoods and people can sort of take more control, and that sort of speaks a bit into energy democracy, and how, so yeah, there's definitely a large scope, not only in terms of sources of production, but also sources of methods of distribution of energy.
Yeah, and that gets to the point that the president raised about different ways that our society can have relationships with energy, and different community and interactions can be quite interesting. Well, I'm guessing we'll talk more about that. Valerie, do we have another question?
We do. What happens to the solvents after they're used to extract oil?
I think that's a question for Elena. So what happens with solvents when you're doing recovery?
When we inject solvents, they dissolve the bitumen in the reservoir, and most of them are produced back. So we can recycle them and inject them back into the reservoir. And this is like a whole cycle. So we're injecting it, then producing, then injecting again, and then producing. So it doesn't stay in the ground. Of course, some proportion stays there, but this is okay because the production is better than nothing. Yes, and of course, solvents are the future probably for in situ bitumen production is by the solvents, because this is like the most environmentally friendly methods of construction.
Okay, thanks for that. Valerie, another question?
Why does Edmonton have such a high carbon footprint?
I think that comes back to you, Neelakshi. Do you have a reason why we are so unenviable?
So two reasons for that. One is this electricity grid that Edmonton takes energy from. So the energy factor or grid factor is pretty high because the sources of energy are mostly heavily reliant on fossil fuels. And the other one is heating. So Edmonton uses a lot of oil and gas for heating its buildings. The cold climate definitely doesn't help. Compared to other cities who have sort of already transitioned to electric furnaces, and where their furnaces are being fed from cleaner sources, let's say hydroelectricity, cities with the same consumption levels of energy have a lower footprint. So those are the two big culprits. There are other smaller factors in terms of number of kilometers that people drive in the city, or the way the city is built, that it's very spread out. So those are the major and the minor contributors towards the larger footprint.
Yeah, I know there's way too much driving around here. Valerie, another question?
I believe this is from Jay's. Are there any sources of renewable energy considered consistent? And I believe that's based on your table you used on your first slide.
So yeah, Jay, you can start there, but we can let anyone weigh in.
Reliable, renewable, and consistent energy sources. Solar and wind power are so far the biggest two renewable energy, and also hydropower. But obviously solar and wind power are not very consistent because the energy input and output, the energy output of those sources depend on the day, where you are, and or even the season. I would say hydropower is more consistent, but it's not everybody has the infrastructure or the water to use hydropower.
Gia, do you want to speak at all to biofuels in the context of stability?
Yes, because we use agriculture and forestry waste, and then we can put them indoors and then do all of the steps to convert them actually eventually into alcohols. So that doesn't rely on any type of weather, as long as we have the feedstock, and we can see there's tons of agriculture and feedstocks there. And actually, the waste, which is from lignocellulose, is the most abundant polymers on the planet. So we have a lot. Yeah.
And though we don't have anybody on the panel tonight who is working on our geothermal research theme, that is another potential source of sustainable, consistent renewable energy. But of course, the geothermal energy is only available in certain areas. One of our research themes is looking at the geothermal resources in Western Canada and Northern Canada and seeing what reservoirs are out there. and then also developing technologies that can be used to harness those particularly low temperature differential resources. So if you want to learn more about that particular type, just check out the Future Energy Systems website. Valerie, next question.
For the life cycle analysis, how does this project differ from current industrial standards of life cycle analysis? Furthermore, what will encourage the industry to start conducting and building their designs for better life cycle rather than a cheaper economic cost?
Well, that sounds like a question for Maggie.
Yeah, thanks. That's a great question. So the big thing that differentiates our research project from a life cycle analysis done in industry is that we're doing it on technologies that are not yet fully developed or commercialized. So in industry, you might do a life cycle analysis on something that you're using so that you have a better idea of the inputs and outputs for that technology. But we're trying to do it on something that has only partially been invented yet or so far. So to see whether that, it makes it more difficult because the information and the data isn't there already. We're creating that as we go. And to answer your question about how organizations make decisions, that's a really good question, something that's really important. And I think that even having these conversations about what is important and what we want our future to look like, the fact that we're having these conversations, at least here, means that we're not just focused on the economics, we're focused on these other social and environmental issues in conjunction with the economics. And I think that organizations will, like some will be more economically inclined, but others will see the huge potential there is to align something that's economically viable with that is also socially and environmentally viable. And as that becomes more valuable to organizations, it becomes more prolific or more ubiquitous, and more organizations are going to be looking at technologies for more than just what the bottom line dollar is going to be from them.
And just on the life cycle analysis, one thing that I'll say, something that sets Future Energy Systems apart from some other programs, is that we have people starting that LCA process while these technologies are being figured out in the labs. And so we actually, in many of our research themes, we will have, whether it's economists or anthropologists or sociologists, working closely with technical researchers, sort of finding out where the pressure points might be, and then getting out and into communities and talking to people about those things now. Because the traditional way may have been, somebody develops a technology, publishes about that technology, and then a researcher from a different field will read that publication at some point, and then they might do a study on it. But now we've got different groups interacting with each other quite frequently. Maggie, I don't know if you want to speak to that. You work in the land and water theme, and that's a very integrated research theme.
Yeah, I actually wanted to thank you, Kenneth, for bringing that up, because I also think that an important point related to our research project is we're trying to figure out which of these technologies are the ones we want to go ahead with and we want to invest or help the researchers invest in them so that they can become commercialized. So that's a really important point and something that that we're trying to do in our integrative theme. So thanks, Kenneth, for adding that.
I know, Neelakshi, at points you've mentioned that it is somewhat unique as a social scientist to be involved in an energy program, but do you see value when you're out talking to community leagues to say that you're part of a group that is sort of transdisciplinary the way Future Energy Systems is?
Absolutely, because I think the community league model is a good combination of technology and science coming together, technology and society coming together. Because there is definitely, so they need up-to-date information on what are the latest or the most applicable technological trends, but then the social scientists come in and say, how could it become more interesting for people, or how could it be further diffused into the community? So it's a good model to study to see how these two trends come together. And they also, a lot of community leagues actively, or the members of their sustainability council actively engage with some of the talks that Future Energy System hosts in libraries and so on, and also engages with other researchers that are part of Future Energy System.
So that's two social scientists saying that it's a good thing. Do any of our natural scientists want to talk about the involvement of social scientists in your research? Or, Gia, when you're working towards getting something into commercialization, is it important, do you think, for us to be involving economists and business professionals and community researchers to know more about what the public is interested in?
Yes, yeah, it will be very important to access the techno-economic part. Actually, that was part of my plan in the future, is we want to do some techno-economic analysis, and hopefully maybe also working with Maggie to figure out the life cycle assessment, and also maybe get her support for future commercialization. Yeah, we want to work with them.
This is one of the secret reasons we do these events, is because we get to introduce people from different research groups and they get to see each other's research and then hopefully collaborate. Elena, Jay, did you want to weigh in on this, or should we go to another question? I think we'll go to another question. Valerie?
All right, this one's for you, Kenneth. Is the financial input directed to the future energy systems from the Alberta government?
Okay, so our funding, the $75 million that the president mentioned, is from the Government of Canada's Canada First Research Excellence Fund. So it's all federal funding from the tri-agencies. So that means that it came from a combination of SSHRC and NSERC funding. So it's all granting council money from there. We don't have any direct funding from the Government of Alberta at a program level, but many of our research projects will be collaborating or have received grants from the provincial government, depending on the topic and depending on whether it fits with the particular research priorities that different departments in the government will have. So many of our researchers have very close relationships with either Alberta Innovates or individual ministries, but not at a program level. Next question.
How far is your project from implementation? What's the timeline until we could see it in action?
Well, that's a good question. I guess we can talk about sort of where we are on the TRL level, or how fundamental or how applied our research is. But I'll start on the technical side, I guess. Jay, I think your research is fairly fundamental. So how far from implementation would you think it would be?
So I work with so I developed catalysts for zinc air batteries, and zinc air batteries actually have been commercialized. So they're being used as those button batteries for hearing aids as well as watches. Now the biggest issue is the lack of cheap and efficient catalyst for it to be recharged. So that's where I come in. So nowadays my catalyst can cycle for 200, 300 hours, which is equivalent to 600, 700 cycles. If you think about your phone, how often you charge your phone, let's assume it's once a day. And let's assume the battery maintains about 80% of its original capacity for 2 years. So that's equivalent to 600 and 700 cycles. So on that, from that perspective, we're quite close to commercialization.
So Gia, I'll come to you next. Obviously, you've been scaling up from Flask. So what stage are you at in terms of the process?
We are actually trying to optimize and work on a more advanced system in the lab. And everything from now on is at least a 5 liter bioreactor. And we have been also getting lots of attention and attraction from industries, especially the ethanol producers. And we're also getting lots of attention from the other fermentation industry, not necessarily alcohol. So the technology is very interesting, and we want to, later the stage, we can try on the scaling up. And after that, it will be maybe a pilot scale, and then before the actual commercialization.
And Elena, obviously you're working on optimizing for reservoirs. So does that mean you are providing advice to producers, or are you producing models that they may ultimately adopt?
We are producing models that can be adopted and used everywhere, but most of the time we are solving real problems. For example, now I am having like a real model, which even can't, I can't even run it on some computers. So, for example, I need to upscale that, and engineers most of the time needs to upscale some models too. So I'm developing the upscaling technique, which will be very helpful as for my team and for engineers in the industry in general. So, and the same with my teammates, they all do some researches, which is very close to the real production needs and to the real engineering needs. So it can be used like in some computer models, model simulators, and or separately as a independent project.
Very good. So, I mean, different type of implementation, but Maggie, in terms of the LCAs and sort of making those decisions, where are things at?
Great. Actually, it's a good timing for that question because we've just concluded phase 1 of our project, which is creating the first versions of the maps that I displayed during my presentation. And that was a big, important first step. And we're moving into phase 2 now. In fact, we have our very first interview on Thursday. And that is to go into the labs and actually talk to these researchers to, one, make sure that our map is correct, but also to help us understand how they understand their technology and the role of their technology in a future energy system, as well as the ability or the desirability for them to commercialize that technology.
Excellent. And then Neelakshi, how do you want to define implementation and where are you at?
Our project is more transdisciplinary in nature. So we worked with community leagues right from the beginning of the project. So the leagues provided us with a lot of data on what were the experimentations that they did. Now it's our turn, and by the end of the year, we are supposed to provide them back with a report of the surveys that we conducted in the community to understand how the neighbors felt about seeing solar panels on their community buildings and so on. So that would conclude the first stage of our research. And then over next year, we intend to work closer with community leagues and draft plans at neighborhood levels to sort of set a roadmap for achieving low carbon neighborhoods. So that's where we are at.
Excellent. Okay, Valerie, I think we're ready for another question.
All right. For the self-cycling fermentation, what kind of automation software or technologies are you using to help improve productivity and reduce labor?
That's for me. Okay. So it's just a common software called LabVIEW. It's a software platform. So you basically you can use that platform to edit and build anything you want to control your program. To control my system. So I actually spent about 2 years to work with electrical advisor at the University of Alberta. We spent time together to figure out what kind of program we want to build and how to debug everything. And at the end, we made it. So the software program is to control and monitor the process. So the productivity improvement is actually because of the process itself. So if we have this automated software to monitor and control everything and to indicate the different stage of the fermentation, that means you have much less labor to actually stand there, take samples, and analyze the fermentation. So with this automated software and the process, we can not only control the process, but also reduce the labor work required. Hope I answered your question.
Sounded like a good answer to me. Okay, Valerie?
Do you feel your work could be easily implemented in poorer parts of the world? Developing countries currently have rapidly growing carbon footprints, and those are expected to accelerate more. How accessible do you feel your research is to developing nations?
Well, that is an excellent question. I think actually I want everybody's perspective on that from their own points of view. Gia, you just had an answer. Why don't you go first? I think I'd be fascinated. Do you think agricultural wastes from developing countries could be used to generate biofuels in the alcohol space?
I think so. I'm from China. I know back home they do a lot of. They also want to convert those agriculture and forestry wastes or any other type of resources into valuable products like the biofuels. China is also working a lot to try to reduce the carbon footprint. And yeah, I list in my home area where it's a big agricultural province. They're taking actions on that.
Jay, do you think developing battery technology will help sort of rural or developing countries when they're trying to implement decentralized energy?
I do think that the battery I'm working on is zinc air battery, and the main raw material required for this type of battery is zinc. And zinc can be found in basically everywhere, unlike lithium-ion battery, which uses a lot of lithium and cobalt. Cobalt concentrates in the Republic of Congo, and the lithium concentrates in South and North America and Australia, China, but a lot of countries do not have access to those resources. So definitely zinc air battery will be more accessible to everybody.
Elena, I'm interested in your perspective on reservoir optimization, and would the models that you're working on be useful in some of those developing countries where they're developing a lot of oil?
I'm not sure about my particular model, but I suppose that developing the industry in general in Canada will help to other countries too, because we are trying to make our fuel more accessible to other countries. And most of the time, developing countries using the same fossil fuels like coal to produce electricity. And this is obviously less environmentally friendly than natural gas. And if we will make pipelines and if we will start transporting this, our like more greener energy to these countries, it will help to reduce the global greenhouse emissions in total. Because, for example, Canada has our climate policy, and among the leading oil producing and exporting nations in the world, only Canada has climate policies. And it's hard to expect that countries without these policies would invest anything in technologies to green their production. That's why if the countries will buy oil or gas from Canada, this will obviously lead to lowering greenhouse emission in general. And we need to help these countries who produces a lot of emissions by burning coal.
Thank you. That makes sense. So Maggie, I'm going to now jump over to your side. When you look at it from that business perspective, are you seeing technologies you think that could be exported to some of these countries?
Yeah, so to give you a bit of context, the technologies that we're looking at are specifically designed to clean up pollutants that are in this case caused by oil or in oil sands process water, but these are pollutants that could exist in other tailings ponds, for example, as well. So I think it's really important that this kind of technology gets developed because, in actually a very similar way to Jay, the technology in biochar, for example, is based on straw and wheat and canola. And for the chicken feathers, that's something that is available in, I think every country of the world probably has at least a few chickens. So I think it's really, it could be really beneficial for all people of the world. So that includes developing nations too.
Very good. And then Neelakshi, I think, well, I know you and your lab's research looks a lot into different community relationships with everything from homelessness to human rights. And then on the point you raised earlier, you alluded to earlier about the democratization of energy. What do you think about the potential implications for developing world communities of having different types of energy systems available to them?
So yeah, I completely agree that developing countries are sort of benefiting from the lessons that are being or have been learned in other countries already. So for example, again, Western nations went through this whole cycle of industrialization and centralization of energy, and now we are moving towards decentralization. If you look at certain communities in the developing world who are having access to electricity now for the first time, they can leapfrog through the process and start off with having microgrids and so on, and access to cheaper forms of energy because of mass production. Prices of, for example, solar panels are coming down. So definitely there can be sort of gain. But I think we should also look at the problem from the other way. So what can Western nations learn from what are called developing nations? And I think there's a lot can be learned in terms of philosophy. For example, Mahatma Gandhi said that there's enough in the world for everyone's need, but not for their greed. So I think there's a lot of philosophical interchange that can happen, that can sort of more developed nations can reflect upon higher footprints or higher consumption levels and the like.
Yeah, and I think one thing that I've found fascinating, I mean, my own background is in the study of history, so one thing that I have found fascinating with your group and some of the other groups working in the social sciences and looking at different community models of energy ownership, for instance, in Canada, is that there are those sort of lessons that are coming here, and I think there's a lot for everyone to learn in this conversation. I just saw a note come through from Colleen, our MC. She's really curious to hear more about those chicken feathers you mentioned. Maggie, do you want to just give the elevator pitch for what the chicken feathers are all about?
Oh, so I'm more on the business side, and we have an actual chemistry expert as part of our team. So he's handling the nitty gritty of those details. But I'll do my best. And that's these chicken feathers are processed very extensively, as you could see from the LCA, to become like a sort of something that you can put in the sediment of the wetland, so that when the water passes through it, it picks up pollutants like, I don't want to say specifically in case I get it wrong, but really important pollutants to get out of the water, so that as the water continues through that system, it's cleaner than it was before. So pollutants that could be harmful for species in the environment as well as human health.
And just because I had the good fortune to research some of the to interview some of the researchers who are working on that original technology. They originally developed the technology to remove arsenic from water. I think it was originally in Pakistan that they were working on it, and now they are looking at that technology for oil sands processed water. It's pretty remarkable. Anyway, Valerie, another question, please.
For Jay, how can electric cars be more widely purchased and driven? It seems like there are limited options for charging stations.
If we look back 200 or 300 years ago, there wasn't a lot of gas stations in the world either. So definitely it takes time for us to build the infrastructures. And also the cost of electric cars and the cost of battery are going down, while the mileage of the electric cars are going up, which is a good sign, and making them more compatible to modern society and more competitive in comparison to petrol and gas car.
Thank you for that. Valerie, do you have another question?
For Elena, what is your opinion on using cognitive technology, AI, ML, to reduce the environmental impact of traditional oil and gas?
Particularly for machine learning, and this is like new. These machine learning techniques are breathing new life in oil and gas technology, and this is true. Like, for example, for a drilling rig, it generates like gigabytes of information daily, and like we have new technologies like fiber optic installed in the ground. So we're constantly receiving a lot of information, and the same is pipelines. If we do sensors everywhere to check the information which comes from these pipelines, we cannot process it without like by hands. We need some technologies to just use all this information, and by use this machine learning and data analytics, we can process this without humans. So we can train computers to quickly identify the problem and to respond to it quickly. And at least it can signalize the engineer that it needs help or it has some problems. So this is like the future is for behind this data analytics and machine learning. We see it now everywhere. And of course, petroleum industry is one of the leaders in this application of these machine learning techniques. And it also helps the environmental to produce oil more environmentally friendly, because it is easier to optimize, because we can use this machine learning to solve the problems quickly and to find the best solution, which we may lose before because of the impossibility to process all this information that we have now. So obviously this will help us.
I can just comment sort of more at a program level for future energy systems. We've got machine learning and AI to a certain extent, but really machine learning integrated into many of our research themes. It was actually at an event like this one in person a few years ago that a machine learning group in our Department of Chemistry, Dr. Arthur Marr, encountered a machine learning group in our Department of Chemical Engineering led by Dr. Arvind Rajendran. And they met up, not having realized they were both using machine learning for two different applications. One was for solar cells, one was for carbon capture and storage. And shortly thereafter, they started doing machine learning workshops. They had researchers in from microbiology. They had resource economists in. And so machine learning is really starting to help a lot of our different research groups get a handle on huge amounts of data. And it has been genuinely accelerating research outcomes. There's some stories on the Future Energy Systems website where you can see, for instance, Dr. Jillian Buriak, one of our leading solar researchers, talking about how using machine learning was able to accelerate outcomes. I think she saw a 30% increase in the efficiency of her organic solar cell technology in the course of a few months, once she turned a bunch of lab books over to machine learning researchers who then used it to train computers and then do machine learning to find different alternatives for materials for those cells. So machine learning is a big story inside Future Energy Systems, and it's one that you will hear from us a lot. So anyway, another question, Valerie?
We have lots more questions, so we might not be able to get to all of them. If we do miss your question, make sure you check out the Future Energy Systems website, because you'll find many of those answers there. But our next question, how does creating alcohol help the environment?
I'm sure there's lots of ways people could answer that question, but I'm going to turn this one over to Gia.
I believe Maggie will also be able to answer this, and maybe even better than me. What I do is so alcohol, especially the alcohol produced from waste, if you think from a life cycle point of view, so thinking about the production and the final consumption, compared to gasoline or other fossil fuels, we are having a lot less greenhouse gas emission, especially the alcohol produced from agriculture and forestry waste. So if we can improve the productivity for the alcohol industry, and then we are producing more alcohol and we're also reducing the cost, that way it can be a lot more cost effective so that we can use more alcohol. Because especially the alcohol produced from the agricultural forestry waste, they're not very cost competitive. That's why we want to improve the production, especially the productivity, to reduce the cost, so that people can use more, and then we can contribute more to the greenhouse gas emission reduction. Thank you.
So Maggie, Gia wanted to hear your perspective on that.
Yeah, thanks. I think that what Gia is talking about is really like the foundational idea behind a life cycle analysis, is that you do it to understand what the inputs and the outputs of the entire process of the entire life of whatever product it is are. So you can look at the whole picture of what inputs and the whole picture of what the outputs are, and understand the kind of impact your technology has. And that's important because, for example, you might find that alcohol is a really good alternative compared to some of the other alternatives for fueling your car, for example, because the inputs are smaller or the outputs are smaller. And I think, yeah, I think that's kind of what you're getting at, Gia, right?
Very good. I think we've got time for maybe 2 more questions, especially if any of them involve everyone. So Valerie, do you want to count us down?
All right, our next question. Is there any research being conducted on using IT in implementing and using modeling and data analysis of inefficiencies in current energy systems?
All right, well, I can Yeah, short answer is yes. We've got a number of researchers in the computing science department, and then researchers actually scattered throughout our themes looking at everything from how the Internet of Things, so to speak, will help with control systems for energy, and I don't know, how different control systems for different renewable technologies that are more intermittent. I don't know if anybody here has research that's specifically IT related. Seeing shaking of heads. Okay, so you get the cheap answer from the moderator, sorry, but yes, we do have research going on inside Future Energy Systems that does involve our computing science department and is looking at different aspects of IT.
I can speak for now. I suppose that everybody in the group has to have some computer-related knowledges. Like before, it wasn't possible to be just an engineer and to know just the processes, but now you have to do all the computer modeling stuff. And without this knowledge, you can't even study in the master's program, because you always need to program. And so computer knowledge is very important, and so now it is hard to diversify between specialists in computer sciences and normal engineer.
And I'll build on what Elena says, just to mention that even in the School of Business, we're starting to see more and more computer machine learning and working with big data is an important part, and the use of Python. Like I've used Python before, even though I'm in the School of Business. So it's getting to be everywhere in the university, and it's really important.
Yeah, and I think actually that was one of the, getting back onto the machine learning train, but the machine learning stories that we write are about people in the Department of Chemistry or Chemical Engineering or Microbiology or in the Faculty of AILS. So there's a huge range of different processing power that's going into all forms of energy research. Okay, Valerie, I think we are pretty close to having to wrap up. So is there one sort of grand question that I can pose to all of our panelists that they can give good final answers to and make everybody leave feeling uplifted?
All right, we have a great uplifting question. How can the everyday person contribute to a more viable energy future?
Well, that is an uplifting question. So I'll make the rounds. I'm just going in the order that everybody's on my screen again. So Gia, I would like to come to you first. How do you think every one of us can contribute to a viable, bright energy future?
Less driving, or try to support the alcohol use to supplement part of the gasoline for your car. Yeah, I mean, with the COVID, it's hard to take the public transport that often, but at the end of the pandemic in the future, please try to take more public transportation.
Very good indeed. Jay, I'm going to come to you next. What do you think about everybody's contributions to our energy future?
I completely agree with Jay's answer. Taking public transportation is definitely much more energy efficient overall. And I also think when the weather permits, we could ride the bike more and walk more, and instead of driving. So that would definitely cut down our fossil fuel consumption and overall carbon emission.
Elena, next to you, what do you think about things that each of one of us can do to help our energy future?
I think that it is in our hands to consume less, to live simple lives, and to recycle as much as we can, to walk or ride for short trips instead of using our cars, and of course be responsible. And I think that everybody who have houses can make their houses more energy efficient, to stay warm longer and to use less electricity and less water. This is everybody's responsibility.
Absolutely. Maggie, I'm going to come to you next. What do you think about the role each one of us can play?
So I'm from a business school, so I'm going to talk money. I think that you need to be really thoughtful about where you spend your dollar, and you want to spend your money building the future that you want. So I highly recommend shopping and eating locally, like supporting local businesses. I think that's really important, and it means that whatever it is doesn't have to travel as far to get to you. So there's some environmental benefits there. And I also want to point out that all of the ideas that have been talked about are excellent and also save you money. So taking public transit, using your bike, making your home more energy efficient, or even switching over to, there is a local totally renewable company that does energy in Canada or in Alberta. So think about where you spend your money and make sure you're spending it building the kind of economy and energy system that you want to see in the future.
Money talks. Neelakshi, I can't help but notice that many of the things that were just suggested seem like the sort of behaviors that community leagues could promote or that we in our communities can adopt. So, I mean, obviously I want your perspective on what each of us can do, and then also if there's any comment about the point you made in your video about how the little actions that each one of us make are the way we hit those international targets.
Absolutely, Kenneth. I echo what everyone just mentioned, small steps. So no one is too small to make a big difference. I think we should always remember that. And definitely start with yourselves. If this means something to you, be active in your community leagues, join social movements. There are many community-led movements in Edmonton, in Alberta, in Canada that you can be a part of. Vote wisely, if this is important for you. And finally, just remember that the energy transition that we are talking about is as much of a technological change as it is a social change. So be part of both of them.
Fantastic. Well, I want to thank all of you for making it seem like we planned to end on an uplifting note. It was very seamless. Good job, everyone. I also will, before I turn this back over to Colleen, shamelessly promote the fact that Future Energy Systems has a lecture series in partnership with the Edmonton Public Library. Before COVID, it was actually happening in person at branches of the Edmonton Public Library. Now it's happening on Zoom. You can find the information for our next public lecture on the Future Energy Systems website. It is next week. It is with Dr. Dominic Savageau, and he's going to be talking about a different approach to biomass, and that is using methanotropes to create products, useful products from, basically these are bacteria that eat methane and turn it into something, either jet fuel or bioplastic. So he's going to be talking about that process. That's next Wednesday night. So you'll find the information on our website, and we have frequent events, and we also have our YouTube channel where some of the people who you've seen tonight and many others are talking about their research. So there's plenty of stuff going on at Future Energy Systems. Like we've said, there's more than 650 graduate students working on all aspects of the energy transition. You've met less than 1% of them tonight, but you've met an excellent less than 1% of them tonight. I don't know if that just sounded weird, but I want to thank all of you for excellent presentations, for excellent discussion this evening. And I will turn it back over to Colleen to wrap things up.
Well, thank you very much. That was certainly educational, and I will never forget the whole chicken feathers thing. That was terrific. So I do want to thank our panelists for your time tonight, for sharing your expertise and being willing to answer so many questions, and to our audience for your very thoughtful questions. There were some I'm afraid that we didn't have time to get to, but obviously an engaged and intelligent audience. So I do encourage you to take advantage of some of those links that we provided during the chat. Check out the Future Energy Systems website and feel free to contact them if you're interested in learning more about any of the research, how you can be involved, how you can learn more. Just reach out to them, and I'm sure Kenneth and Valerie would be happy to point you in the right direction for more information. That wraps up our evening. Thanks very much to our sponsors, TD Insurance and Manulife. And thanks to everybody for joining us. Enjoy the rest of your evening.